A small lab in Hungary. Not CERN. Not some billion-dollar detector buried under the French-Swiss border. A relatively modest nuclear research institute in a city most Americans can't pronounce. A nucleus was excited. It released energy. An electron and a positron flew out. And then the pattern broke. At one particular angle, the data rose when it should have fallen. A bump appeared in a graph that should have been completely unremarkable. But if that bump is real, it points to something physics does not have room for. A new particle, a possible fifth force of nature, and a mass that keeps coming back no matter what atom they use. 17 million electron volts. For more than a century, physics has been built around four known fundamental forces. Gravity shapes planets, stars, galaxies, and the large-scale structure of the universe. Electromagnetism gives us light, electricity, chemistry, almost everything we interact with in daily life. The strong nuclear force holds quarks together inside protons and neutrons, and binds those protons and neutrons inside atomic nuclei. The weak nuclear force governs certain radioactive decays and plays a crucial role in how the sun actually burns. Four forces. That's the entire known framework. The Standard Model describes three of them with extraordinary precision. Gravity sits outside it, handled by general relativity. Together, they are the basic language physicists use to describe everything. So a fifth force is not a small adjustment. It's not a missing footnote. It's a new line in the grammar of reality. The story starts at Atomki, the Institute for Nuclear Research in Debrecen, Hungary, with a team led by physicist Attila Krasnohorke. They were studying beryllium-8, which is unstable but can be created briefly by firing protons into lithium-7. For a fraction of a moment, the nucleus jumps into an excited state, then drops back down and releases energy, sometimes as a gamma ray, sometimes as a pair of particles, an electron and a positron. A positron is the electron's antimatter twin, same mass, opposite charge. Physicists can predict exactly how those pairs should behave. The electron and positron come out at different angles, and the number of pairs should change smoothly as the angle changes. Because in the Atomki data, the curve did not stay smooth. At wide angles, around 140 degrees, there was a clear excess, too many electron-positron pairs flying out in that direction. One way to explain that shape is that something else formed first, a short-lived particle created inside the nuclear transition, existing for an instant, then decaying into the electron and positron the detector actually sees. When the team reconstructed the mass of that possible particle, it landed near 17 mega-electron volts. That's where the name came from, X17. The X means unknown. The 17 is the mass. And if X17 exists, it's deeply strange. Much heavier than an electron, but far lighter than a proton. Neutral, fast decaying, and completely absent from the Standard Model. A particle like that doesn't just casually appear in a nuclear transition without something carrying it. Something new would have to be interacting. That's why theorists started paying attention. The most explosive idea was that X17 might be a new boson, a force-carrying particle. Photons carry electromagnetism. Gluons carry the strong force. W and Z bosons carry the weak force. So if X17 is a boson, the question becomes brutal. What force is it carrying? One proposal was especially strange. X17 might be protophobic. It means the particle would interact only very weakly with protons, while coupling more strongly to neutrons and electrons. That matters because a normal new force would already be in trouble. If a 17 megavolt particle talked loudly to ordinary matter, decades of previous experiments should have seen it. So X17 can't be obvious. It has to be quiet. Interact enough to show up in a very specific nuclear decay, but weakly enough to slip past everything else. That's an incredibly narrow hiding place. Too visible, and it would already be ruled out. Too invisible, and Atomki should never have seen it. X17 sits in the thin space between those two walls. Then, the same number appeared again. The Atomki group reported a similar anomaly in helium-4. Different nucleus, different transition, same electron-positron pattern. Again, the mass came out near 17 mega-electron volts. Then carbon-12, again an excess. Again the same mass region. Beryllium, helium, carbon. Different nuclei, same ghost. A single anomaly can be a mistake. A repeated mass scale is harder to wave away. But there's a problem. The strongest claims still come from the same experimental tradition. Similar detectors, similar methods, similar nuclear pair creation measurements. That doesn't make the result wrong. It makes the next test obvious. The signal had to be reproduced somewhere else entirely. That's the only way an anomaly becomes physics. MEG2 at the Paul Scherrer Institute in Switzerland used an entirely independent detector setup to look for the same X17 signature inside the same lithium to beryllium reaction. MEG2 did not see the clean excess the simplest X17 picture would predict. That doesn't erase the Hungarian measurements, but it means that if X17 exists, it's not going to be easy, broad, or simple. Then Padme attacked the question from a completely different direction. Instead of recreating the nuclear transition, Padme used positrons hitting electrons in a fixed target. The logic was clear. If X17 can decay into an electron and a positron, then under the right energy conditions, an electron and a positron should also be able to produce it. So Padme scanned the energy range where a 17 megavolt particle should appear, not through the same nuclear transition, but through resonant production. A different doorway entirely. After analyzing an enormous dataset, Padme found its most interesting deviation near 16.90 mega-electron volts, very close to the X17 mass region. Not a discovery, but not nothing either. So where things actually stand. Atomki sees a repeated nuclear anomaly. MEG2 doesn't see the simple version cleanly. Padme sees a modest excess near the same mass from a completely different method. 3 experiments, 3 different approaches, 3 different answers that don't quite line up. The reason this matters goes far beyond one particle. Galaxies rotate as if extra mass is present. Galaxy clusters bend light more strongly than visible matter can explain. The large-scale structure of the cosmos appears to have been shaped by something real, massive, and completely unseen. We call it dark matter. We don't know what it is. X17 doesn't automatically solve dark matter. That would be too convenient and almost certainly wrong. But a light particle that barely communicates with ordinary matter could be part of what theorists call a hidden sector. A set of particles or forces that don't interact with us in the usual way, but still shape the universe in ways we can't fully account for. If X17 is a messenger between ordinary matter and that hidden world, then the Hungarian bump isn't just a nuclear physics puzzle. It's a crack in the wall. 17 mega-electron volts. Small enough to hide. Big enough to break the map. There are a few book recommendations in the description if this kind of physics keeps you up at night. And on the end screen, 2 more videos that go down the same rabbit hole. Thanks for watching. See you in the next one.